rolling this morning. What I want to look at today is we're going to look a little bit at fuel properties, and yeah, I see you smiling, so something oddly appropriate about this for this evening. So yeah, we're going to look at fuel properties today, setting you up for a lab on Wednesday. So we are going to do a lab, and we'll be in your small groups again, the same as last week. So groups A, B, C, starting at 8 o'clock or whatever. So we'll do that. Basically, the bottom line is Wednesday we're looking at different fuels, alternative fuels, and how the engines perform on that. So that's what we want to talk about this morning, is to get that enough background and everything so you know what you're doing for that. Okay? Makes sense? You're good to go. Any questions before we launch into that? Questions on homework that's due on Wednesday? Is that going okay? You'll start it tomorrow night? Something like that? Yeah, okay. Those things will burn you if you wait too long. So let me actually mention one thing from the homework that I did not talk about in the lecture videos. Hello? That's not what I have over here. Why'd you go to sleep? Okay. Wake it up. Better. All right. So let's give this a try. All right. So one of the things I talked about in the homework, I asked you to do in the homework, and a couple of those problems, is looking at torque rise or torque reserve. So two different terms used for the same thing, torque rise and torque reserve. So if we go back to our torque versus speed curve, it looks something like this. You collect the data in the lab, so we got the governor control zone, governor max here, and then we get a big curve that'll do something like that. Now, most of you had data, look pretty good like that. I've seen a couple of data sets. People asking me about the labs for Wednesday. Looks something like that. Most of you had a little trouble. It's hard to get this data experimentally once you pass this peak torque point up here. So once you hit your peak torque and you're trying to roll off to the left there, it's really hard to keep the dynamometer going without the engine stalling, and so most of you have data going up to the peak, and that's kind of the end of it. So something about it in there. So that's what you looked at, okay? Now, what the book talks about there, we actually measure this torque rise or torque increase. So if I go from this point over here, and I'm going to talk about what that is in just a second, which one of those points. But we look at how much the torque increases from this point over here up to its maximum. That's what we call the torque rise or torque reserve. Two terms, you'll see two different terms used, either rise or reserve used for that. Tell what you do that. Okay. Torque rise or torque reserve, looking like that. Okay. It's actually measured as a percentage. And it's measured as a percentage of the rated point. So some point over here where our rated torque is. Okay, for an engine. And remember we talked about that. It's like, okay, there could be three different points that are all happening kind of at the same corner, very near that region over there. So we talk about a rated point where engineers have decided this is what we're going to specify as the rated performance for that engine. So that could be, we could choose anything we want, but typically it's over and around there. That might be the peak power, and they all might be kind of close. And then we talked about, for tractors, there's a typical speed where we get the right power takeoff speed, where that power takeoff is going right at 540 or 1,000 RPMs. And so there could be like three different points, and actually on a lot of your the tractor test reports that you were looking at, what in the world is going on here this morning? So on those tractor test reports, you get all three of those. So what the torque rise is officially rated at is rated at the it's measured from the rated point. That'll wake up. There you go. See how long it lasts now. Okay? And it's a percentage. And so you can calculate the torque rise, so TR, torque rise or torque reserve, based on a percentage. It's just basically the peak torque minus the rated torque at rated speed, if you will, or rated performance, divided by the rating. So it's just a percentage above that rated torque, whatever that rated point is. Okay, so, and this actually becomes it's a fairly significant performance indicator, and people look at that for a lot of engines carefully, because that torque rise, the torque reserve, and how far to the left it is will tell you how you can utilize that engine. So, and we don't have time to go into a lot of the performance differences and stuff like that, but gasoline engines, spark ignition engines in an automobile or something like that typically do not have a whole lot of torque reserve. And that peak torque happens pretty close to the rated point over here. So a gasoline engine is going to have, its performance might come up, and let me change my colors here a little bit. So a gasoline engine might do something like this, where I'll get a torque rise and it'll look something like that. So its curve is going to be a lot shorter. The peak is not going to go quite as high, but big heavy engines that we need for agriculture, for over-the-road trucks, for construction equipment and stuff like that, we need that lugging ability. We need that engine to be able to do heavy work and to be able to drag things and work hard and stuff, and not worry about high speeds, high engine speeds and stuff like that. And so that's where in those kind of engines you're going to see that longer curve going to the left. You're going to see more rise, more reserve out of it, and that's going to be desirable for that kind of performance. Okay, so a lot of different shapes of curves that you'll see with a lot of different engines, depending on the application, depending on what you need it to do. Okay, does that make sense? Follow me that. All right, got a couple head shaking here, so we're doing good. It's Monday morning, we're still waking up. We're all right. Okay. So that will help you with your homework. So let's move on. Fuel properties. Let's spend a little bit of time because we're going to measure fuel. So we're going to pour cooking oil into the engines down there. So literally, we're going to go down to Kroger and buy oil, and we're going to pour it in there and see what happens. So it sometimes becomes an adventure for us, depending on what the temperature is and stuff like that. But that's what we're going to do and see what happens. So we're going to look at how the properties of that fuel are going to affect the performance of that engine. And that's what I want to talk about and get to today, is an understanding of how, kind of a prediction. So we ought to have an idea of what might happen when we go down in the lab. So let's take a look at what fuel properties might affect that and start thinking ahead of time. This is what we predict was going to happen. Let's see what actually does happen on Wednesday. Okay, so that's where we're going to go. So we're going to look specifically at, and we're really going to focus on the energy content, so how much energy that fuel has in it. And I'm going to break some things. We're really going to focus there, and these two things, the energy content and the ignition properties of that fuel. So you go to the gas pumps, got an octane rating, which fuel do you buy, the regular or the high test or whatever. So what different octane? Why do you choose the different octanes? That's what we're going to look into. Okay? Those kind of things. And a little bit about flowability. So those are the two primary things we're going to focus on that really have a big impact on how engines are going to perform. Okay? With me? Good? All right, so fuel properties. So let's start with spark ignition fuel. So typically, spark ignition engine, what fuels are we using? We're either using gasoline or ethanol typically, so an alcohol. All right. So, and there's some of the properties there, the key properties for it. So the energy density, and these are slides I put together for a extension talk, so they're English units, but the number is not as critical as the relative numbers that we want to look at. So we're looking at BTUs. What's a BTU? Wake up, tell me. What's BTU stand for? What is it?
British thermal unit.
British thermal unit, yeah, so it's a measure of energy density. What would it be in SI units? What would energy density be? That's a good question. What's the corollary to BTU in the SI units?
Kilowatt?
What's that? A kilowatt.
What?
A kilowatt, now remember watts, has a time factor in it. So Newton meter per second, yeah, so it's going to back the time off of it, so close. So it's not the watt, because that's how much we're using, you know, how much energy we're getting out of it, and or much power we're taking. But the energy that goes in is without the time factor, and that's the Newton meter. So a joule or a calorie, you know, same thing as the joule. So a joule or a calorie, Newton meter are the units of that. Okay, so that would be the SI units, and then it would be per gallon. It could be per weight, you know, it could be per kilogram, per pound, something like that. We can measure that a lot of different ways. But the energy content, how much energy density, how much density we have in a certain quantity of the fuel, okay? So that's the density. The other thing is the octane down there, all right? So this is the one that kind of throws people for a loop, because racing engines, anybody into racing, drag racing, NASCAR, all that kind of stuff, what kind of fuel do they use in those engines? Any idea? The high performance stuff. They using gasoline? No, probably not. What are they using?
E85.
E85, or probably maybe even E100. Okay, so what is E85? That's 85% ethanol. Okay, so that's what that means. E85 means 85% ethanol, 15% probably gasoline. So it's a blend. This would be pure ethanol. So they may be using E85. They may be probably are going to be using pure alcohol. Okay, what about the energy content? It's kind of funny because you listen to announcers, you know, all the rednecks on Fox or whatever on NASCAR, you know, they talk about this high energy racing fuel. Is it high energy? What do you see in there? Does the ethanol have more energy? Heck no, not nearly. Okay, so the density of gasoline is 115,000. You know, ethanol is 76,000, so quite a bit less density. Why do they use it? Why do they use it?
Octane.
What's that?
Octane rating.
The octane is very different, okay? So when you go to a fuel pump, typical octanes for your vehicle, all right? Most of us put in the cheap stuff, right? What is it around here?
87.
It's 87 typically is what we get, right? If you want to pay a little bit more, you know, get the 89 or the 90, what's the highest? And it varies in different pumps, but usually what, 93, something like that, sometimes 92, somewhere in there. So yeah, maybe up to 95. So 87 to 93. What's ethanol? 117. Oh. So there's a big difference there. All right, so we're going to come back and talk about octane, because that's pretty critical to making those engines get the performance out of them. Okay, so, and that's going to tie in closely with what you looked at on the videos for today on those PV curves. You remember those thermodynamic curves? You know, I threw that up there and you went, I thought it was done with thermo. I hated that thing, right? Here it comes back, right? So that's what we're going to look at, right? So typically, you know, in our fuel pumps, you don't buy pure ethanol in our fuel pumps. You go to other countries, you do. You can go to Brazil and buy pure ethanol. So you can actually get pure alcohol to put in your vehicle. So there's a whole bunch you go to a pump and there's like 6 or 7 different choices of what you're going to put into your vehicle in other countries, specifically in Brazil that I'm familiar with. So there's a lot of variations there. Typically what we have available is either gasoline. Some places you can find E85. Okay, and again, that's an 85% blend of ethanol. That's why we say E85, 15% gasoline. All right, so most all of our gasoline has at least 10% of ethanol in it. Okay, so most of it. You can get non-alcohol gasoline, so you can get gasoline that does not have the alcohol in it, does not have ethanol in it, but it still has to have something else. So there's this MTB, methyl methyl tetralbutyl ethylene or something like that. I forget what it stands for. It's not that important, but that's a petroleum-based additive that they put in the fuel, and it's put in as an oxygenator. Okay, so what does that mean? As an oxygenator. And we did some examples looking at the combustion equation in the videos. Yeah, you watch that. So what happens in that fuel? What's the typical makeup of those fuel molecules? What did you see on there? So I think I used the example I did in class was diesel, wasn't it? So what molecules were in diesel? So what did it look like?
Carbon and hydrogen.
Yeah, primarily carbon and hydrogen. So there's C, something, H, something, whatever. But when we have an oxygenator in the fuel, we're going to add something to it. And alpha ethanol has oxygens. When you look at the chemistry of it, and it scares the heck out of me because chemistry was a long time ago for me, but you get these little oxygenate hydrogen, or I forget what they're called, but these little things stuck onto the molecules that have oxygen in it. So you're going to have some type of an some oxygens in there, a number of oxygens. Okay, so it's an oxygenator for the fuel. How does that help us? How does having oxygen in the fuel help us in the engine?
You get cleaner emissions
Okay, why? Cleaner emissions, why?
because you don't need nitrogen. You don't need air.
You don't need as much air. Yeah, so when I pull air in, what am I pulling in with the air? Mostly, right? Mostly nitrogen is what's coming into that engine. And the oxygen comes with it that I burned, so I got that nitrogen. So the nitrogen is in there, and then it gets hot, and it combines with the other stuff, and you get nitrous oxides and all the weird stuff coming out. And we'll look at emissions later on. We'll spend a little more time talking about where that comes from. All right, but that's where it is, okay? The other thing is, think about how that, I want to burn that fuel. So that fuel comes into the engine, and it's either drawn in as an air-fuel mixture in a spark ignition engine, or it is injected into the engine in a compression ignition engine. But I'm relying on that combustion process. And what does a combustion process do? So chemically, what's happening? It's taking my fuel molecule, which is carbon, hydrogen, maybe some oxygen, combining it with what? What's it reacting with? In that reaction equation. So this molecule plus what? In the reaction equation. That was on the video this week, wasn't it? Yeah, okay. Now remember, was this thing plus what?
Oxygen.
Yeah, plus the oxygen, yeah? So there's going to be, there's hydrogen there, but mainly what we want to add oxygen to that. So we want some oxygen, and I'll say, K or whatever, put on. I'm not going to worry about subscript at this point. We're going to take that fuel molecule, we're going to react it with some oxygen, and then hopefully what do we get out of it? So ultimately, what should we get out of that? The ideal process? What are the molecules we should end up with when it combusts, when it burns, when it reacts? Same thing. What's that?
Water.
Yep, so it should have water. And what else? CO2, yep. Carbon dioxide, yep. That's what I should end up with. So that's that reaction process that should be happening. Okay, so the key is, going back to what's got to happen in that combustion chamber, I've got that fuel molecule, or a whole bunch of them in there floating around. I want to have them mixed really well so that when that starts to combust, when the heat gets up and the pressure gets up high enough to make this reaction start to happen, I want to make sure that when this fuel breaks apart and I've got carbons that are free and starting to look for some partner or whatever, I want to make sure there's enough oxygens there, that there's carbons all find two oxygens to go home with. Okay, so to go out of the engine with. So I want to have that all mixed together. So I rely on, in the design of the top of that piston, if we look at the top of pistons, they're never flat. So there are always domes, there's always different shapes, all that. And it's to create turbulence, to create air movement, so I get really, really good mixing so that all those fuel molecules have oxygen molecules very near them, so when they combust, they burn efficiently and I don't end up with COs. You know, if there's not enough carbon, not enough oxygen around, that carbon's only going to grab one oxygen, then I have carbon monoxide, that's bad. Or maybe there's no oxygen and I have carbon going out, we call that soot. That's black smoke coming out of your vehicle, that's not good, okay? So, or I have, there's nitrogens up there that are going to grab the oxygens. The nitrogens that come in with the air, they grab the oxygen, so all that. So I want to have lots of oxygen right close to the molecule. Well, if I can have oxygen in the molecule, I guarantee you that it's right there. So the oxygen would be right there so that I have a better chance of that combustion process ending up with clean water and carbon dioxide, which I guess we can question whether that's clean, greenhouse gases or something like that, but it's certainly better than carbon monoxide or the nitrous oxides that are going to come out of the thing, okay? So that's what we've got to have in there, so I want to have that mixture. So that's why we have, and all that to go back to this, what is an oxygenator? It's adding oxygen to the fuel to make that thing burn a little bit better, okay? I'm going to give you guys a homework question next week on the next homework where you look at top fuel dragsters. So have you ever watched drag racing, you know, those cars that go a quarter mile in like 3 seconds, less than 3 seconds, it's just absolutely nuts. But you look at that engine technology there and the fuel that they use, it's a very highly oxygenated fuel. And we'll look at the air-fuel ratio required for that thing, you're going to be absolutely mind-blown with that fuel. Okay, so, but how do I get oxygen to it? So it's that whole combustion process. So that's what I want you guys to be thinking about with engines. You know, too often we kind of go to the back end and kind of memorize what's happening or whatever. I want you to think about that combustion process up front. And as engineers, a good engineer is going to be thinking about how do I make that fuel combust better, recover more of that energy to do the work that I need it to do. Okay, makes sense? So that's where we get good. That's where we have innovative and good solutions to problems, is understanding the root of what really should be happening and ask ourselves what isn't really happening out there. Okay? All right, enough preaching. Let's get back to this. Is that over the final? Yeah, it's over the final thing. All right. So that's what we got. There's a lot of vehicles we buy now are flex fuel vehicles, so you can put pretty much any fuel in it. And actually, 2001, from the year 2001, any vehicle manufactured after 2001 has got to be able to handle up to 20% of oxygen in the fuel, so 20% of ethanol in the fuel. So, so any vehicle that's 2001 model year or newer, I can put 20% in it, and it should operate just fine. Okay. Now, there's a lot of places where we don't want the ethanol in the fuel. Right? Any of you got background or grandparents like, I don't want that alcohol in my fuel or whatever. You just get some people to talk about that. All right. Marine applications are one place where ethanol can cause us a problem. Any idea why? You go to marines, you go to boats. If you got a boat, and especially if you have fuel supplies on the water, you know, you got boats that you don't put on a trailer and fill them up at the gas station. You actually keep them in the water, and there's fuel supply in the water. That fuel supply is not going to have any alcohol in it. Any idea why? All right. What are fuel tanks made out of? What material? So in your automobile, what's it made out of? Any idea? Anybody ever have to change them? Get underneath there and kick them? What do they sound like? Do they go doing? Do they go thunk? Where do they go? Like so. Typically, they're made out of steel. Typically, some of them are made out of some plastics. We have some plastic material. All right, but typically made out of steel. So on a boat, why would I not want to put steel? Why might I want to put some other type of material on a boat? That has to go in the water. That has to float. So, do I want heavy steel, or might I want light aluminum or fiberglass or something like that? And so what you run into with aluminum and fiberglass, ethanol likes aluminum and fiberglass. And I mean it from the standpoint of it likes to eat it. likes to corrode it. That's not a good thing, right? So a lot of alcohol in fuel supplies can damage some equipment. And so we're going to think about that. We're going to see that with biodiesel as well as we go through some of this discussion here, where biodiesel can cause problems with some components on engines and stuff. So we have to think about that. So there are places there where that ethanol can be a problem in the supply. Even the blend of ethanol in our fuel supply can cause us problems. Okay. Good so far? Questions about that? All right. So, yeah, let's see if I can change slides. There you go. So that was spark ignition fuels, compression ignition engines. What do we typically stick in them? Typically it is diesel fuel. Let's see. Oh, come on. So typically diesel fuel. Of course, we're seeing a lot now more biodiesel. Where do we get biodiesel from? That was a big rage, 5-10 years ago. The biodiesel rage, and fuel prices went up, and everybody's like, where were they getting their fuel from? Where were they starting? Get down to McDonald's, get the French fry oil. A lot of people were building these conversion kits. We had some here. People started doing it and asking us questions. So extension folks were building these things and trying to cook diesel out of vegetable oil and French fry oil. We're pulling it from the deep fry oil from the dining halls and stuff like that, and experimenting with it and see what you can do. Right. So you get this biodiesel, but it's basically a biological product. It's a diesel product that comes from oils. So, and that's basically what we're going to be using on Wednesday, is a biodiesel, but it's just not going to be refined. So we're going to take a vegetable oil, canola oil, or whatever we happen to get for cheap down at Kroger. It's going to be some vegetable-based oil. It'll be a vegetable-based oil, canola, sunflower, something like that. And we're going to burn it. So chemically, the structure is not a whole lot different. It's just longer chains that we break up chemically into shorter chains, but real similar chemical makeup, and so it'll burn, right? So there's some other variants on this. Of course, we talk about number 2, diesel fuel. That's the common thing that we get in our supply. You'll see a lot of places where there's kerosene. Ironically, that's the fuel that's used in a lot of jet applications. So it's kerosene. So it's considered from ground land-based vehicles as kind of the cheap fuel, the cruddy fuel, but that's what we use in jet engines. So some different fuels like that. But there's some differences there. I don't have anything up there on kerosene, but let's look at number 2 diesel fuel, energy density, comparing diesel to biodiesel. So it's a little closer than what the ethanol was, right? So the ethanol was quite a bit lower than the gasoline. So biodiesel is not as dramatic of a difference there in terms of energy content. Physical density is pretty much the same, but the cloud point is very different. Any idea what the cloud point is of a fuel? Can you take a guess? What do you think? Fuel clouds up. Talk about a fuel clouding up. Actually, we talk more so, and I grew up in a little further northern climate in Pennsylvania, so we had trouble in the wintertime with our fuel gelling up, which was basically the same thing as clouding up. So what is it, Trey? You're shaking your head.
It's basically diesel. If it gets too cold, starts to turn into a solid instead of a liquid.
Yeah, so it freezes, basically. That's essentially the process. It doesn't go to a complete solid. It ends up in like a gel state, so like Jello. So it will come out like like a gooey Jello, nasty kind of thing, and it will not flow through pipes. So the fuel lines and stuff on a vehicle turn into a solid, and you're done. And it won't pump the fuel, and so you either heat it up or do something to try to get it flowing again to be able to make your vehicle operate. All right, so cloud point is pretty critical. Look at the difference in the biodiesel at the cloud point, and there's a huge range. So this is Fahrenheit, that's degrees Fahrenheit. So that biodiesel will gel up at a fairly cold temperature. So think about cooking oil. You ever take cooking oil camping? Anybody go camping in the wintertime when it gets cold? And what will happen to your cooking oil sometimes? You ever have it turn into like Crisco, shortening? So that's what it'll do. It'll cooking oil will actually turn into a consistency of shortening. So it's the same kind of a process where you go from that oil that's liquid that'll flow into something that looks like Crisco shortening, that white gel stuff or lard or whatever we bake with, right? So that's what it does. So that can be a problem for us, and so we have to think about fuel supplies and managing them. And in Kentucky, it's not as critical in our climate. We do get cold and we have occasional cold spells, but not long-term cold spells. But in northern climates, there's a very different fuel supply that you receive in the wintertime that's going to have different additives in it and everything to make sure that this cloud point stays low and doesn't end up at a point where that fuel is going to gel up or freeze when it should do it, when we're trying to operate the engine, because that can't operate. Okay, so the cloud point is pretty critical for us to think about. Here's the thing. So look at the range on that. So what's kind of interesting when you look at what constitutes diesel, it can be a lot of different junk. Okay, so it's really the standards, and we talk about standards for how you define what is classified as diesel. Those standards are really broad. When you go to gasoline and standards for gasoline, the standards are very tight. So when you go to a pump and different manufacturers, different brands of fuel or whatever, it's going to be very tight. There's not a whole lot of variation from one fuel to the other. So they're all going to be very similar. Cloud points and all that kind of specifications have to be very tight. When you go to diesel fuel, it's kind of wide open. And so this is something where you really got to watch suppliers. People that manage a lot of fuel really have to work closely with their suppliers to understand, hey, if I'm buying fuel in September, am I sure I'm going to burn all this fuel before wintertime, or do I need to start buying wintertime fuel because I may be holding this to January and February when I'm going to have trouble getting that fuel to flow and be able to use it. Okay, make sense? So understanding that fuel supply, understanding some of those components of it is pretty critical. So, vehicles, when we fill them up all the time, we don't think about it, but that fuel supply does change. So even with most of your suppliers, most of the fuel pumps, gas stations and stuff, there will be different fuel that they'll sell in the wintertime. It won't be as drastic of a difference in southern climates, but in northern climates, it does change. And it's kind of transparent. Most people don't realize it, but it does change. Okay? So something to be thinking about and be aware of, right? So, and again, this was a couple years ago. Biodiesel was a big thing, so there was lots of blends and people were paying attention to it and worrying about it and all that kind of stuff. I'll show you some weird things that it does to vehicles, to engines. We've ran into some issues a couple years ago with some of these blends, and I'll share some stories of that. But basically, we blended again, like the E85, if you see a B and a number, that's the percentage of biofuel that's in that. So most of our supply, what we're going to be using in lab, the supply we're getting out of our pumps right now, as far as I can tell, is a B5. So it's a very low blend of biodiesel. And it is an oxygenator, so that does add some oxygen into the fuel, into that diesel. So it does serve as an oxygenator. It also serves some other things that give us some lubricity and stuff like that. So I'll come back and mention that. Occasionally you'll see blends up to B20, but when we do that, we see some weird things happening. So I'll come back and we'll show you what the biodiesel can do to us. All right? Good from there. So how much power loss am I going to see? So I put this together for farmers, like, okay, I got this tractor out here, all these fuel suppliers, and this was, again, 5 or 10 years ago, all these fuel suppliers are trying to sell me all this biodiesel junk, and is it going to use it? Is it going to hurt my tractor? Is it going to avoid the warranty? What's going on? Yada, yada, yada. So here's what we told them, is that with B2, it's probably not going to be noticeable. If you got B20, you're going to see about a 2% performance drop. Are people going to notice that? Maybe, maybe not. If you get up to B100, you're going to see a 10% performance drop. That you're going to notice. Okay, but performance drop, what does that mean? And here's one of the things that you're going to try to figure out on Wednesday for our engines down there. There are really two things that could happen when I put a different fuel into that engine, and maybe a combination of those two. So what could happen? Let's say that I'm going, like we're doing on Wednesday, I'm going to take biodiesel, we're going to run the engine, we're going to understand what the performance curve of that engine looks like. Then we're going to stick this cooking oil in. Okay? Cooking oil has a lower energy content, energy density, lower energy density. So what would I expect to happen on that engine? What performance difference would I expect to see? Could I expect to see? What do you think? Power curve from one, how's the power curve from the other one going to be different? Any ideas? Am I going to get as much power out of it with the lower energy density fuel? What do you think? Drew, you're shaking your head. You think no? Everybody's afraid to commit. We don't know. All right, let's wait till Wednesday and find out, right? No, let's think through it. So what do you think? If there's not as much energy in the fuel going through the engine, am I going to get as much power out of it? What was logic tell you? I mean, if there's not as much energy there, I'm probably not going to be able to get as much power out of it. So there's a good chance that I'm going to see a performance drop in that my torque that I measure is going to get lower, or the power output then is going to be lower, so it might change that. It might change the shape of the curve a little bit. It's kind of hard to tell, but we might see the shape of the curve. But that's one thing that I can probably expect. Lower energy density fuel, I won't get as much power out of it, unless something else might happen. So we didn't think much about the flow rate of fuel going into that engine, right? So the energy density is measured in BTUs or calories per gallon or pound or however, whatever unit, however we want to measure that. So the amount of fuel that's going into that. So what is the chance that that engine would just burn more fuel? And then maybe the power wouldn't change as much. I wonder how that fuel pump works on that engine. I wonder how it's going to react to a different fuel. How's that? What do you think the difference is in the physical properties of that cooking oil and diesel is going to be? Any guess on that? Viscosity going to be the same? No, probably not. What's that cooking oil going to be? Which way? Viscosity going to be higher or lower than that, probably.
Pretty high.
Pretty high, yeah. So it's going to be thick. I mean, you pour cooking oil out, you get this glug thing, you know, kind of slow. You pour diesel, maybe, you know, a lot of it may not handle diesel, but it's pretty similar to gasoline. You spill gasoline on the side of your car, it's pretty thin. It runs, it's more like water. So there's going to be a viscosity difference. Might that respond differently going through the fuel pumps, through the fuel system on the engine? Possibly. Okay, so there's a couple things that could happen, and really two different things that could happen. I could have a lower power because there's a lower energy density in there, but that engine might be handling that fuel differently. It might actually get worse because it's a thicker fuel. The flow rate might go down, plus the energy content going down, so it may have a much lower fuel, much lower output. Or the engine, because of the way the governor works, the governor might open up a little sooner or something like that, and it might actually move a little bit more of that fuel through it. I don't know. I'm not sure what's going to happen. But those are the things that could happen, and that's what I want you guys to be thinking about as we go and look at that engine. Which one of these is really happening? So what's going on? Is it more flow, less flow, more power, less power? What's happening? So that's what we're going to try to evaluate. Does it make sense? What we're looking at? So those are the questions that you want to be looking at. Make sure you've got enough data to be able to answer all that. Okay? Now, can I predict that a little bit? So I can. So let's think about it. So if I have a lower energy density, you know, forget about fuel flow rate and all that other complicating things. If I just look at the energy density of one fuel ratio to a second fuel, so I'll just call that E, the energy content. So energy density, energy content, however it's measured, of one fuel to another fuel. would it be reasonable to say that the performance should somewhat follow that same ratio? So the performance, or I'll put a P maybe for power, so the power I get from that one fuel, that ratio should be the same as the other fuel. So if I've got this fuel on top, E1, that has twice the energy content of E2, would it be reasonable to assume that I get twice the power from that engine that I would from the other one? So, maybe, maybe not. And that's one of the things that we want to look at. So I asked you to say, hey, does your performance difference, any performance difference that you measure, does it make sense based on the energy content? Look at something like this. Look at some ratios and say, okay, energy content is this much lower, so is the power that much lower? Does it make sense mathematically? Can I kind of, do a thumbnail sketch? There's no theory in this whatsoever. This is just let's take a ballpark shot at it and see if it makes sense. I don't know. Let's try an example. Let's look at fuel economy. We'll go back to spark ignition engines now. So there's your F-150. Oh yeah, compensation truck right there. All right, good. Nice thing there, 2017. Got some data. So you can look up data on this fuels.gov, fueleconomy.gov. So all that fuel performance data, we talked about Kevin was in there barking that they all lie about their performance data because you never get what you have. They don't lie necessarily, but there's a standard that they test too. But they report E85 and gasoline. So let's try this thing to see if it works. So let's look at E1, energy 1 to energy 2, and see if that makes sense to the performance of that same fuel, a performance ratio, performance 1 and performance 2. Let's do it based on fuel economy. See if we can predict that, okay? So, gasoline and E85. So what is the energy of gasoline? So if I back up 2 slides, energy density, and I don't care what units are because it's a ratio, so we're just going to cancel out. So, whoops, that's compression ignition. There's the gasoline. So gasoline is what, 115,000? So 115,000 divided by, and the sparking of the ethanol is what, 76,000? And let's look at my city mileage. Let's just take that one for example. Should be then equal to 18. So the performance of gasoline we said is 18 miles to the gallon. And that bottom should end up to be 13 if that ratio holds. Let's calculate that. Let's calculate what the performance would be just purely based on the energy content difference in the fuel. Let's just make an estimate of what that fuel mileage would be. So if you calculate that, some of you get calculators out, do the cross product, 76 times 18 divided by 115. I ended up with X to be, I think, 11.9. You agree, Trey? You got one up?
Give me a second.
So 18 times 76 divided by 115. Skipping the zeros. Do old professor math. Is that what you're getting there, Jared? Yep, so you got that number. All right. Does it make sense? What did they test it at? They tested it at 13. What did I calculate? 12. All right, it's in the ballpark. It's not exactly right, but it's in the ballpark. And that certainly doesn't consider, aerodynamics of that vehicle, city mileage and stuff like that, starting and stopping and those kind of things. There's a lot of other factors in there, but it does give me a bit of a ballpark idea of what's going to happen there, the different fuel contents, the different energy contents, and how that fuel is going to respond. So that's kind of a quick and dirty way to kind of look at it and get some predictions of what might happen. Again, when we're going into the lab on Wednesday, all this stuff helps us so that we're not just going in, we blindly collect a bunch of data, we go home and work it up and say, oh man, that doesn't make sense, what's weird going on. If we go into the lab having an idea what's going to happen, and we see something weird going on, that's when you can stop and say, hey, wait a minute, is something not working right? Or maybe this is really what's happening, maybe something really weird is going on. And you're going to be a lot better at doing data collection, doing field experiments and stuff like that, the more that you have an understanding of what that system is doing, how it should respond, what you're kind of expecting, and then when you see the unexpected, then you're going to know, okay, is this really unexpected, or did I screw up somewhere? Okay, makes sense? So that's what we're trying to do. That's right, what we're trying to come up with here, and what I'm trying to get you guys to think about in terms of data collection in the laboratory and stuff like that. So hopefully you're learning not just about fuels and engine performance, but you're learning a little bit about data collection and field experimentation, those kind of things. Okay, got it? Sneaking that stuff in. You make us learn extra stuff. Yeah, we'll make you learn extra stuff. Okay, make sense? You got that? So, higher math, all that calculus is killing me, man. All right. I'm teaching small engines class to community leadership development folks. That math does kind of blow them away, so it's kind of interesting working with that group. A very different skill set. Yeah. All right, let's get back to this. Octane and cetane is two different things. So we have cetane number. We don't rarely talk about that, but there's cetane rating for diesel fuels as well. Okay, what is octane? Octane or cetane, both of them, they quantify the auto-ignition properties of the fuel. What's auto-ignition? What does that mean? Auto-ignition. Spontaneous combustion. That was a big thing when I was a kid. Everybody's worried about people might spontaneously combust, you know. So, where that came from. Science is interesting over the years, right? So it's kind of spontaneous combustion. So the deal is, I take fuel, mix it with air, you know, get that vapor thing, and I squeeze it. And I squeeze it hard enough, eventually when I squeeze it, it's going to ignite, it's going to burn. Okay? And we often will say, well, it's going to explode. It doesn't really explode. It burns really fast, so it kind of acts like an explosion, but it's different than an explosion. It's a burning, it's an ignition. So it's a burning front. So we've got to think about this thing burning, think about this fuel burning. It burns very rapidly, but it doesn't explode necessarily. Okay, so we've got to kind of change our mindset a little bit about that. But that's what auto-ignition is. If I squeeze it hard enough, if I squeeze that fuel hard enough, it's going to ignite. Okay? Is that a good thing or bad thing? Good thing. Landon says it's a good thing, right? Why is that a good thing?
It's what it's supposed to do.
Is it? And spark ignition engines? That's a trick question. What do you think? Yeah, a diesel engine and a compression ignition engine, yeah, it's really good. Okay, so that's how I get it to ignite. So in that compression ignition engine, do I compress the fuel? When that piston's coming up, what's in that piston on the compression ignition engine? What's above that piston? Air or air and fuel? Air. In a compression ignition engine, I don't put the fuel in there because I'm going to compress that fuel, or compress that air, and get it above the auto ignition pressure of the fuel. Then when I stick the fuel in there, when I inject the fuel in there, the pressure is already high enough and it burns right there. And I get that ignition. So I control when it happens by when I stick the fuel in it. Okay? Now, in that spark ignition engine, what am I compressing? Air and fuel, right? So if I compress that, and before that piston gets to the top, I'm still compressing, I exceed that auto-ignition property, the auto-ignition pressure of the fuel. Drew's laughing, what's going to happen? It's going to burn. Now I've got a problem because the piston's coming up, the momentum of the engine, there's usually a flywheel, there's some mass to that engine, it's trying to drive that piston up, but I've got that fuel that's trying to drive the piston down. Things ain't working right, and the engine sounds really bad. You get a rattling in your engine. Maybe some of you have experienced that. An engine is going up a hill, especially if your engine speed goes down. That engine will rattle and bang and make all this rattling noise. It sounds terrible. It sounds like it's going to fall apart. And that's what's happening, is that fuel is burning. It's kind of fighting against that piston that's coming up. I'm not getting an efficient burn in that cylinder because it's burning at the wrong time. And so that's when I get this rattle bang. We call that engine knock. So that's the official term for it. But it's this rattling, banging, knocking the engine because it's burning at the wrong time. So when do I want it to burn? I want it to burn not until that piston gets to the top or pretty close to the top, and I ignite it with the spark. So, the trick question, is auto ignition a good thing? Sometimes. It depends on how you're trying to eliminate that fuel and what you're trying to do. Make sense? You with me on that? Is that kind of putting some of this together from the videos that you've seen? All right, so how do we measure that auto ignition property? Well, you've seen the octane rating on gasoline. So, for the gas pumps, the higher the octane, the higher the ignition pressure. So the more octane I get, the higher the octane number, the more I can compress that fuel before it burns and ignites and gives me my power stroke, okay? Cetane is just the opposite. So again, on a compression ignition engine, auto ignition is good because I want it to burn, okay? And this can be a real problem because that pressure, it's actually a combination of pressure and temperature kind of goes with that. You know that ideal gas law, you remember that from way back then, PV equals nRT. When I compress a gas, the pressure goes up, but what happens to the temperature when I compress a gas? What's that? It's going to go, yeah, it goes up when I compress it, okay? So if I have a high pressure and I release it, so that's when we think about that. So like if you have a high pressure tank or something like that, so like your propane tank on your grill, and you let that gas out of there, it's cold, okay? Or not, actually sometimes in cold weather you get frost on a little propane tank. It's because that gas is expanding so the temperature drops. So there's a temperature tied to that pressure. So when that pressure goes up, the temperature goes up, and then makes that whole thing try to burn, okay? So, you know, all this stuff is going on. Temperature and pressure, it all is combined in there. There's a standard way to measure that. Believe it or not, there's cetane numbers. You get a cetane number for diesel. You never see that on a pump because you got one pump for diesel and you get whatever you get out of it. But if you're buying fuel from a supplier, you can get different cetane numbers. That's what you want. So on a cold engine, when I'm starting up a diesel engine, I don't have a lot of temperature in there because that engine hasn't been warmed up. So I'm relying on just the pressure of compressing that gas above the piston. So sometimes it's hard to get the pressure high enough because I don't have the temperature helping me with that increase in pressure to get it above the auto ignition properties of fuel. So sometimes it's pretty difficult to start an engine, to start compression ignition engines, just because when they're cold, I don't have that pressure there to be able to get above the auto ignition pressure of the fuel. And so that's where a higher cetane, which is a lower ignition pressure, is going to help me. It's going to help that fuel burn a little bit better and help that engine to start. So a lot of diesel engines, especially if you've got older tractors and stuff like that, when you start them in cold weather, they hammer and knock and make a terrible racket until the engine warms up, and then they'll smooth out. And that's what's happening, is that ignition pressure is barely high enough to ignite the fuel. It may not ignite right away. It may ignite a little bit early, a little bit late. It does some weird things until the engine gets up to temperature and until it runs a lot more smoothly. Okay? So, cetane helps us. Lower ignition pressure is better there. All right? So, let's break this down again and make sure you really understand this. And by the way, there is a conversion from octane to cetane. So, they're like continuous scales. So you can actually convert one to the other. But, you know, those numbers aren't that critical to us. I'm not worried about it. So, here's the deal. All right? It's not related to energy content of the fuel. So, if I go to the pump and I've got a vehicle that runs really well on regular gasoline, doesn't sound bad or anything like that, and I put high octane gasoline in my engine, will I get better gas mileage out of it? What do you think? That's something that you want. I'm going to challenge you. Does anybody have a vehicle that requires higher octane fuel? Anybody in here have one? So everybody's bought their own car. You haven't spent money on the Mercedes and the higher end vehicles that require. So why do they require higher? So it's not related to energy content. And we go back to those racing engines, I mentioned that, racing engines use ethanol. Ethanol is a much lower energy content, but it's got a higher octane. How am I getting more performance out of a lower energy fuel? Why do those performance engines, those performance people, why do they want alcohol, ethanol, with the octane in it? Okay, so higher octane, this is what it means down here, but let's think what's happening in that engine. Okay? PV curves. Here we go. You kill me. Thermodynamics. Pressure, volume. What do they look like? Remember? You do this number, this number, this number, something like that. Okay? And I'm a bad artist, but that's the idea. Okay? So what are the different cycles there? Different cycles on that. What's going on the different parts of this curve? So I'm going from here up to here. What's happening in the engine? Volume is going down. Pressure is going up. So which one of those cycles, which one of those strokes in that engine is happening? What is that? We need to remember what those 4 strokes are. What are the 4 strokes on an engine?
Intake, compression, power, exhaust.
There you go. Intake. So we got to get fuel into it. So on a 4-stroke engine, the piston comes down, pulls fuel in. Then we've got intake, air, either air or air and fuel comes in. Then what's next? Intake, compression. I compress the fuel. Then what happens? What happens after I compress it?
Power.
I ignite it. Yeah, so the power stroke is next. So I get the ignition up there. So I either inject the fuel in the compression ignition or I hit the spark and light it. And then I've got the power stroke. And then I have, what's the last one? Exhaust. I shove the old gas out and then I start all over again. New gas coming in. All right, so this stroke, I start from here and go up to here. Which stroke is that? That's the compression. So I'm taking the fuel I've already had the intake. I've already had the fuel in there, fuel or air fuel mixture, either one, depending on what kind of engine I have. I compress the thing. I get to here. Then I get this real big. That should be a vertical line. I really drew that poorly, but I get a big pressure spike up there. So that's when I've ignited the fuel. So I either injected it or lit it with the spark and it burns. I get the big compression. So that's really ignition in here. And then what's coming down here? What is this? The top part of this curve. Pressure is coming down. Volume is getting bigger. So if the volume is getting bigger, that means that piston is coming down. The volume above that piston is getting larger. So what is this stroke then?
Power stroke.
Yeah, that's your power stroke. That's the power coming down. How do I measure the power from that curve? The power that I get out of, or the energy that I've gotten out of that fuel in that stroke. How do I measure it from that curve? What's that? Somebody said it. Who said it? It's the area. Sure, it's the area between those curves. So this area, not my pen roll, right? So this area between the curves is how much energy that I have recovered from the fuel. So that's how much energy has gone into pushing that piston down. And if I add the time to it and figure out how many times this happens, you know, how fast that's happening, then I can come up with the power. So pressure, volume, look at units. How do the units come out? What's the units of pressure?
Force per length squared.
Yep, force per length squared. What's the unit of volume? Length cubed. So length cubed over 1. What do I end up with? force times the length, which is energy, yeah, torque or energy. So that's work, that kind of thing, all right? So newton meters, foot pounds, whatever, that's the energy. So the area inside that curve is what power I get out of it. Okay, so, now think about the auto ignition pressure of that fuel. So let's say that we're looking at a spark ignition engine. So, gasoline car, okay? Auto ignition pressure. Where does it have to be on this y-axis for that spark ignition engine to work correctly? Or within what range, or what are limits? Tell me about that. The auto ignition pressure for that spark ignition engine to work correctly. Where does the auto ignition pressure of that fuel have to be to make it work correctly? What happens if my auto ignition pressure of the fuel is here? Let's say that it's right there. What's going to happen in that engine? You're grunting.
No, it's going to connect before.
It's going to ignite, sure, because here the pressure in that cylinder at this point is going to pass the auto ignition pressure of the fuel. That's going to make the fuel ignite. That's not good because that piston's still going up. That's bad. So where does the auto ignition pressure of the fuel have to be if this is a spark ignition engine to make it work? Where does it have to be? Up or down? Which way? It's got to be up. Yeah, it's got to be above that corner. So that auto ignition pressure of the fuel has got to be above that point. Or that fuel's going to burn too early. It's got to be above there, so I want to get to that maximum pressure of compression so that I ignite it when I want it to ignite, not when I don't want it to ignite. So that auto ignition pressure has got to be somewhere above that point. Above this level, above that corner. It's got to be higher than that. Okay? Can you follow that? Does everybody understand that? I seem like I'm pulling teeth here on this. Is this just that we're not awake on a Monday morning, or is this are we having trouble getting our head wrapped around it? Okay. So, going back to the racing engine. Well, let's just forget about the auto ignition. We know where the auto ignition pressure is. How can I get more power out of that fuel? So look at that PV curve. And what is something I can do on that curve? If the curve is the area between the curves, it's the area here, how do I get more power out of it? So to get more power out of it, I'm going to have to expand that area, make it bigger. So how would I do that? What would that look like? What do you think? What could I do to get more power out of it? I'm building a racing engine. I want more power. How do I get more power? You watch the tool man, haven't you? I'm going to blow it up, right? I might blow it up. What the tool man always did. What could I do?
You can add more volume.
More volume, okay? So what are you going to do to add more volume?
Make it bigger. Bigger.
Just a bigger engine, okay? So what I'm going to do then is take this curve and stretch it out this way. Yeah, so I could do that. So I could add more volume down here. But if I add more volume, what's that going to do then when I compress it? So if I've got more air in there, what's that going to do to the pressure when I compress it? We got to think about both ends of it, right? So physically, what's happening? Physically, what's going on? So let's look at the volume. So this volume is the volume above the piston. Everything that's above the piston, this whole head space is kind of an odd shape. You know, the piston is cylindrical. So around piston, and it moves so far, it's easy to calculate the displacement. So that's how much volume is displaced of that engine. I think I talked about that, didn't I? Did you see that on the video? What do we call this volume up above that piston? When it's all the way to the top, what do we call what's left up there? We have a name for that. The clearance, yeah, so the clearance. So that volume that's left on the top is the clearance. That's the clearance volume, right? So where's that on the PV curve? Where is that on the PV curve? So volume goes from here to here. This volume difference from here to here is the displacement of that engine. So that's where piston goes in, pulls air in, pushes it out. That's compression. So that's what goes out. That's the volume that is displaced by the piston. So this is the volume that's displaced by piston. This doesn't go to zero. So what's left down here is my clearance volume, right? So that's my clearance volume, right? So this is the clearance. All right, so when I was a kid, muscle cars was a big thing. So old, 70s, 80s, big sedans, big V8 engines. So everybody was building muscle cars, souping them up, getting more power out of them. Now with all the electronic controls, you got these little mosquito things running around. But back then, it was all about the hardware. It was all about the engine. It was all about doing some modification to the engine to get more power out of that engine, to get more performance. And one of the common things that we would do on engines is what we call shaving the head. We would shave the head, okay? Now, this is going a little bit more than what the content was there. Any idea what the head is when we talk about the head of an engine? So the head piece, the head. So the head is the top that bolts on. So you kind of see a joint right in here, right? So the top of that engine will actually bolt on, and then all the hardware is not shown there. But this top piece will bolt down onto the cylinder block. So this is the block with the cylinders in it, so they'll block down. So what we would do is shave the head. So we would take the heads off of the engine, put them on a machine tool somewhere, and you would physically machine some of the material off of that head. So when you put the head back on, what does that do to what's going on inside of the engine, to the displacement, to the clearance volume, and all that? What's going to happen? So if I shave that head, take a little bit of material off the bottom of this, so when I put her on, it's down closer, what's happening? There's less clearance volume. So I've reduced the clearance volume. Have I changed the displacement? No, the displacement is determined by the crankshaft down here and how far the piston is moving, right? So that's determined by that. So I haven't changed the displacement, but I have changed the clearance volume. So, and I've actually changed the maximum volume as well. So when I pull this down, all the way down, there's actually not quite as much volume up there, but I've made a small change there. So what that's going to do is move this in, my maximum volume, it's going to move it over a little wee bit, okay? But down here on this part of the curve, and let me go to a different color here, let's go to green. So I'm going to move that to the left a little bit. So it's going to move that volume in a little bit. This curve is kind of relatively flat, so it doesn't make a huge difference. But look what happens up here when this curve changes. If I move that over by the same amount, what does that do? So here's my clearance volume. I cut that clearance volume in half or make it smaller. This curve comes way up because it's a exponential, it's a curve. It comes way up before it hits that, and I get a real big spike in pressure, and I open that curve up like crazy. I do something like that with it by reducing that clearance volume. Okay? You see what I did? Can you follow that logic? Reduce that clearance volume because of the shape of this curve coming up. It's going to make that pressure jump up pretty significantly. What did I do? What did I do with my auto ignition pressure? If my auto ignition pressure was sitting here, what did I do? I took my pressure above my auto ignition pressure. What does that tell me about that low octane cheap fuel that I was putting in that engine before? Is it going to work? No. What am I going to have to do? I'm going to have to buy higher octane fuel to be able to get up above to get that auto ignition pressure higher than that corner so that that fuel doesn't ignite when I want it to. So, going back to that initial question, do I get more power out of high octane fuel? In my original engine, moving that auto ignition pressure up without any modification, would it have changed the power output? Does it change that PV curve? No. How do I get more power out of high octane fuel? I've got to have the compression ratio to make that happen. So when we talk about compression ratio, that's the volume, the maximum volume over the clearance volume, remember? So we get that compression ratio. So a higher compression ratio means a higher pressure up here. So I've got to have that auto ignition pressure above that corner to keep that fuel from burning when I don't want it to burn. That's how I get more power out of it. Does that make sense? Are you guys all tracking with me on that? Some of you are answering questions. I see some of you are going, not sure on this. So, my little Mazda CX-5, you know, nothing fancy about that thing. If I get out of the pump and put the real expensive high octane fuel in it, is it going to make a difference in the power of that thing? No. Okay? It's not going to make a difference. Now, if I have an engine that calls for it, and you have higher end vehicles, so like some of the higher end Mercedes, those kind of vehicles, will actually require higher octane fuel. And what they're doing is they have in the engine, they've got more compression ratio. So their engine is ready to do it. And they're doing some other things as well. It's not just as simple as compression ratio. They're doing some other things with air fuel ratios and stuff like that, because they're burning it at higher pressures. They actually are affecting the pressure inside the cylinders. There's a lot of stuff going on that they can utilize that higher octane fuel to be able to get more power out of it. But ultimately, what are we doing? Ultimately, we're trying to expand that PV curve to get more power, because the power is the area inside it. Anything we can do to make it bigger makes it better. Okay? Makes sense? We got through that? Man, that was a lot. That was some theory. You made me go back and look at thermo. You kidding me? Gosh. All that stupid stuff. Anybody not take thermo yet? I think you all had it. Good. All right. Does that make sense? You start to see what engineers have to do. You know, we're not designing engines. I want you to have enough understanding of an engine to know how it works, and know what kind of power we're getting out of it. And we're going to look at the energy that we get out of it and stuff like that. That's what I really want you to understand from this. But I want you to have an appreciation for those folks that do design engines. What are they doing? I mean, they're looking at this headspace on the top. How is that air, what's the turbulence look like? So they do modeling of the fluid dynamics and the particle dynamics in there to see how they're moving and see how that fuel is mixing to make sure I get good mixing. So, you know, and that's happening how many times a second, you know, depending on how fast this engine is working. It's crazy what they have to do. So there's a lot of things like that that go into that design. You know, there's a lot of things going on. All right. So where's the energy loss in an engine? So we talk about engines, and I'll show you this in a little while in another example. I don't think you've seen that video yet, but I go through an example. We look at the fuel that's going into an engine, and you'll kind of see it this week a little bit as well. So you look at the fuel that's going into an engine and look at how much of that fuel that we recover, what percentage of the energy in that fuel that we recover for useful work. And it's like 40% at best. Where's the energy loss on that PV curve? Where's the energy loss? What do you think? Got any idea?
Isn't that what's below the curve?
Absolutely. Exactly what it is. It's what's below the curve. So when we draw red, this is my energy loss. So if this pressure does not get down to zero, it's all of this underneath that curve. That's the energy loss. It's essentially the energy that I have to put into that fuel air mixture to compress it. So that's fundamentally what it is, in addition to friction and some other things. But in the thermodynamic cycle, it's the energy that I have to put into compressing that fuel. That's energy that I can't recover, that I can't get back. Okay? Make sense? So, there's your challenge as engineers. Design an engine that doesn't have this. How do we do that? I don't know. But work on it. Think about what's a better way to do that. There's challenge for you. Questions about that so far? I kind of ignored all of this stuff over here. So higher octane can mean a cleaner burn. So because that, you know, I'm not burning too early, I'm burning at the right time, so I'm operating that engine efficiently, I should get a good burn. I'm going to have less knock and dieseling. So that's a kind of funny term. Octane isn't a spark ignition engine, but we talk about a spark ignition engine dieseling. So we actually had some tractors, old antique tractors when I was growing up. Actually, my family still uses them, old Alice Chalmers tractors. And when it gets really, really hot on a really hot day, and depending on what fuel you have, where your supply is coming from, you turn the ignition off on that engine. It's a spark ignition engine, gasoline engine. It shuts the spark off, but that engine will keep running. Why does it keep running? Because this pressure is high enough that that engine was designed pretty close, and actually we did some modifications to them years ago and actually increased the compression ratio a little bit. And so that auto ignition pressure is running really close. When an engine gets hot, PV equals NRT, you know, like a gas law, all that, the pressure gets up, and so that pressure is right above the auto ignition pressure. So it's close enough that it doesn't really sound bad when it's running, but when you shut the spark off, there's still enough heat in that engine that it'll just keep on running. So it won't shut off. So there's no way to shut that engine off, because those old engines, there was no control on the fuel supply, so it would just keep running and running and running. It never sounded good when you did that. It would hammer and rattle and stuff, but it would just keep running. So you have to put it in gear, let the clutch out, and actually stall the engine. That's the way it shut off. So we would have engines that would diesel. That's not common now, again, because most of our, for safety reasons, anything newer, you actually shut the fuel supply off in addition to killing the spark in an engine. So that's something we do now. So, and we can have a higher compression ratio. That's where performance engines, that's why performance, you know, the racing engines and stuff like that, they're using a lower energy ethanol. That's quite a bit lower energy content, but that octane was like 117 on ethanol, which is way higher even than higher gasoline, 95 octane. So they run very high compression ratios in those engines. And so that's how they're getting the power out of them. They got a very high compression ratio, very high pressures in those engines, and then they can utilize it and expand that curve out like that, so they can really push this up close to zero, make that clearance volume as small as possible, open up that curve, get more power out of that fuel, recover more of that energy. Okay? Making sense? What's happening? Following with me? Good deal. All right. In the compression ignition engines, the higher cetane, that's the lower auto ignition pressure. That means it won't knock as much when it's running slow. It helps with cold starting, so it doesn't need as high of a pressure. You don't need those temperatures to be up for that engine to start. So the high cetane, which is the lower auto ignition pressure, means it starts easier. Maybe higher emissions. Really? Can it burn too fast? So think about that. There's a burning front. Okay? So when I inject the fuel, or when I light the spark in that space above the piston, there is a burning front. So that flame, that burning is going to start, and you're going to have a burning front that moves across that space and moves out through that space. And it originates from either the spark or from where that fuel is injected in there. If that auto ignition pressure of the fuel is really low, and in a compression ignition engine, I inject that fuel in there, that fuel starts to burn right away. Well, it hasn't, those particles, those droplets, the atoms of fuel, have not gotten to mix with all the oxygen in the outer edges of that compression chamber in there. So what will happen is that fuel can burn too fast before it mixes with the oxygen, and just like we talked about a few minutes ago, if it's not getting that oxygen available, that's when I'm ending up with carbon monoxide, free carbon, and other stuff coming out because it can't fully combust. It can't execute that combustion process in there. So sometimes the higher cetane, the lower auto ignition pressure can actually hurt us a little bit because it burns too quick. I need it to mix completely before it burns all the way through. Making sense? So it's a complicated deal. really is. There's a lot of complicated stuff that is happening in the top of that engine to be able to burn that. And what always blows my mind away is how fast that has to happen, how many times a second that all that is happening. So that's pretty neat. Cool. All right. Fun fuel facts. Again, this was an extension presentation I put together for farmers when they started selling all this biodiesel, and farmers were like, oh my goodness, it's going to kill my tractor. What's going to happen to it? So, all right, do I need to modify my engine? So, and this is going back to spark ignition stuff for biodiesel. So they're worried, do I have to do anything to burn this B20 that's coming in? No. So anything up to B20, nothing. But if I get above B20, above 20%, here's the deal. So, and ethanol is kind of the same way. Biodiesel and ethanol, they are really good solvents. If you want to clean grease off of something, take cooking oil. All right? So I do some train collecting, and when we want to we get grease or something like that on plastic cars, and stuff, it's like, how do you clean that with, a lot of solvents and stuff like that will dissolve plastic. I go get oil, I go get olive oil or cooking oil, and rub cooking oil on that grease, and it'll take that grease off. And then that cooking oil is clean, you can take it off the surface. So it's a good solvent. So biodiesel is a solvent. You spill biodiesel on your vehicle, it'll take the paint off of it. So it's a really good solvent. It'll also eat rubber components. So if you have gaskets and stuff like that made out of natural rubber, it'll dissolve them, it'll eat them. So that's a bad deal. So, here we go. Wake up again. So it is a good cleaning. So here's the story. See if that wakes back up. So a number of years ago, we were doing a lot of tobacco research here, and it was actually about time I started a little bit earlier, so it was 20 years ago. So they had this tobacco harvester that they took out to a farm and were testing it on this guy's farm. And the thing was running fine and everything. They worked the first day, it worked good. They went to the farmer's pump, filled up the vehicle. The next day they went out and ran for about half hour or something like that, and the vehicle shut off. So the engine just shut off and quit. So let's let that rest a little bit. So they couldn't figure out what happened when, look, the fuel filter was clogged up. So they got a new fuel filter, took the fuel filter off, put a new fuel filter on. Engine ran great for about 45 minutes, and then it shut off. And they went and looked again, fuel filter was all clogged up, all full of gunk. Put a new fuel filter on, ran for 45 minutes. What happened? The farmer had a biodiesel supply, a high percentage of biodiesel in the supply. Diesel, number two, petroleum-based diesel has a lot of paraffins in it, a lot of waxes that will build up on the inside of the tank, on the inside of the lines and stuff like that on your whole fuel supply system. That biodiesel cleans it. So what it was doing was cleaning all of that stuff that was on the inside of the tank, and it was going into the engine and getting clogged in the filter. So they had to run about 4 or 5 filters through that engine until they finally got everything cleaned off, and then the engine would run a little bit. So it cleans. So that was one of the things that we saw happen early on when the biodiesel supply first started to come in, is that people were cleaning filters and changing filters and stuff like that because biodiesel cleaned everything out. So, but again, it's a solvent. It will clean stuff up and burn it off. All right. So that's the thing. That's a solvent. So the rubber components and stuff like that. Sometimes they're going to change the injection timing, the fuel flow rate, the air fuel mixture. We'll see that later when we do air fuel ratios. That when I have that oxygenator in the fuel, that changes what the air fuel ratio has to be. So that changes the air flow rate, the fuel flow rate. So I'm going to put a different amount of fuel for the amount of air that's going into the engine so that it burns more efficiently. Okay, so we see that with any kind of an oxygenated fuel, that's what's going to change. Okay, so those kind of things change to make it run efficiently, but only at the really high concentrations of that. Other things is, the cool thing is it's non-toxic biodegradable, so you could drink this stuff. I wouldn't do it, but you could actually drink this stuff and not die. It's a great solvent. Yeah, again, watch painted surfaces, fluid replacement. It likes rubber. One of the things that it does do for us is lubricity. So lubrication. All right. So a number of years ago, federal government passed a law that we had to remove all of the sulfur from our fuel supply. So there used to be small amounts, trace amounts of sulfur in the fuel. What the sulfur would do is provide lubrication for the injector pumps and stuff like that that were pumping the fuel through the engine. So there was some lubrication. There's not necessarily oil in those parts where the fuel has to flow through. You rely on the lubricity of the fuel as it's moving through a lot of those components to lubricate those pumps. So they would add a little bit of sulfur in the fuel to increase that lubricity so it wouldn't wear pumps out. Well, sulfur, when you burn it, does bad things in the atmosphere, and so the EPA says, no, get rid of the sulfur out of the fuel. So now what do? We got to have something in our fuel to provide the lubricity that we need for those components in the engine. And so that's one of the things that biodiesel, and that's one of the reasons why you see most of our supplies, at least a B2 to a B5% of biodiesel, is to provide some of that lubricity back. And then it's the biodegradable, non-toxic kind of thing. So that's one of the good things that it does for us, is it gives us that lubricity. So, and you'll see the lubricity of the cooking oil when we pour it in the engine. It's that thick, gooey, oily kind of thing that'll lubricate. Okay, makes sense? So, yeah, fuel supplies are changes. Low sulfur fuel, that was a big deal way back when. Got to have that low sulfur junk, and then people were pouring stuff in their tank, to increase the lubricity, and then there's more emissions going out because of the junk they're poured into the fuel. So it's kind of been a weird thing as we go. Storage, biodiesel has a limited shelf life. Any fuel has a limited shelf life. And the more alcohol, the more ethanols, methanols that we put in our gasoline, the more biodiesel that we put in our diesel supplies. Those oxygenated fuels, they have a very high water affinity. They like water, so they will pull water in. And then they will have that oxygen from the water that will react, and essentially the fuel will rust. So when we talk about the fuel oxygenating, or become oxygenated and no good, so gasoline, if you store too long, just won't work anymore. And part of that is because of the water that it pulls in, that it kind of reacts slowly, same kind of a reaction sort of as the combustion reaction, but that oxygen is breaking down the fuel, and it's no longer a fuel molecule. So we really have to watch water, and you got to think about the shelf life of fuels, how long you leave fuels, right? So, and that can become a problem. We see in our lab down there, a lot of our lab engines we use a couple times a year, and so we have to always be flushing them out and putting fresh fuel in them so they work well. All right, so some practical things. Here's some cool things for you to think about in terms of fuel vehicles at the end of the day. If I want to keep moisture out of my fuel supply, this is what we tell farmers. You've been working out there all day long, it's hot, you're tired, you bring the vehicle back to the barn, you want to just park it and go home, but I'm saying nope. On the way in the driveway, stop and fill that tank up before you park the vehicle. Why? Go back to 447. The psychrometric charts. What do you know about air supply? Think about that air. You're coming in with a tank that is empty, and it's hot. It's been out in the sun. It's been working. There's a lot of heat from the transmission, from the engine. That whole thing is hot. And I park it. What's going to happen? Think about that. Air in the top of the tank. The tank's empty. So a little bit of fuel in the bottom of the tank. What's going to happen? Killing me. We're making me remember all this other stuff. Right? What happens when air cools?
Water in the air is going to condense.
You've got water and air is going to condense. The air is going to cool, so it's going to be a couple things. So think about the air in the tank as it cools off. What's it going to have a tendency to do when stuff cools? When it gets hot, it expands. When it cools, it's going to shrink. It's going to get smaller, which is going to pull it in, and then we're going to get that condensation because at nighttime, the dew point, the relative humidity goes up and the temperature drops, and so we have that, get up close to that dew point. So I'm going to pull cool air into that tank as it cools off. that cool air is gonna have a lot of moisture in it, and then when it gets cool, it's gonna have a tendency to condense on the inside of the tank, and now I've got water in my tank, which I don't want, all right? So why does filling it up help? If I fill it up while it's hot at the end of the day, what's that do for me? Do I have all that big empty airspace in there sucking in? No, so I have very little airspace, so even if it does suck a little bit in, there's not gonna be much moisture that's gonna come in, as opposed to what would come into a large tank that is breathing and pulling air into it, okay? So, think about that, psychrometrics, you know, all that stuff, yeah, put it all together, be an engineer. All right, so keep your caps in good condition. Here's some more psychrometrics to think about. This is kind of good analysis. If you can, put your bulk tanks, if you've got bulk storage, they should be underground. Why?
That won't change.
The temperature doesn't change. Yeah, so I said heating and cooling, heating and cooling, heating and cooling. It's pulling the air in, pushing it out, pulling it in, pushing it out. That's what's bringing moisture into the tank. So if I can keep it from heating and cooling, I'm not going to do that. Underground is the best. Getting permits to put things underground is really difficult and really expensive, so most people don't do that, so they put them above ground. So either a double wall tank, which are really expensive as well, but at least put a cover over the tank, some kind of a shade so the sun isn't heating it up. And what color do you paint your tank? Paint it nice and black so it absorbs all that sunlight? No, paint it white so it reflects the sunlight so it doesn't get hot. Yeah, so paint it white. So there's some things like that, just some fundamental things you can do to manage that fuel supply, thinking about how to keep the moisture out of it. Gosh, we talked about chemistry today, we talked about thermodynamics, we talked about psychrometrics. Well, yeah, all this stuff goes into equipment design. We pull all this stuff together to understand how to design a machine, how to develop those parameters. Okay? Questions about that? That's what we're going to pour in tomorrow, or Wednesday. It'll be kind of fun. Exhaust smells like French fries. It'll be kind of cool. So, except for the one tractor, it has an oil leak, so the exhaust smells like oil all the time. The other one, we'll take a pipe off and it'll smell. You can smell the French fries. Okay? All right, that's what I got. If there's no questions, see y'all on Wednesday. Have a great week. Remember your small lab group times, 8 o'clock, 9:15, 10:30, whatever. I need a new one. Yes, sir. Yep.
One section seems to be nuts.
The
Last week or,
the slides are up online,
okay.
and the video I recorded. Let me shut this off while we're talking. So, you three guys